Hello and welcome to TarGZ. Today we do a jump in the future and we talk about quantum computing. And we do it with Alessandro Berti, postdoctoral researcher at University of Pisa. Welcome, Alessandro.
Hi, Luca.
Alessandro, would you like to introduce yourself and give some context on your research?
Sure. So, hi everyone, I'm Alessandro, and as you already have said, I'm a postdoc at University of Pisa at the Department of Computer Science, and I'm currently I'm doing research on quantum algorithms. Back in the past, I obtained my PhD, still here at University of Pisa, and also for the bachelor and the master degree. I spent some time, 5 months more or less, at Fermilab in Chicago, America, which is, we can say that is more or less a center like the CERN, which is a well-known center that study physics in Europe. So this is more or less my background. In the free time, I had worked for to build a community whose name is Superior Valley. Our aim was to create a bridge between students and big tech company. So to tell them how to prepare for interview at big tech companies. And also I'm still doing podcasting with other two co-hosts, Luca and Eugenio. And this is more or less a summary of myself.
Nice.
But today we are here to discuss about quantum computing, right?
Yeah, sounds super cool. And yeah, what is quantum computing?
Oh. So we know what is a bit. A bit is the most basic unit of information, and it can be 0 or 1. But when we put this bit in the quantum world, it becomes a quantum bit, qubit, and it shows very peculiar properties like superposition and entanglement. And this is, let's say that when you have a qubit, it can be both 0 and 1 at the same time.
Okay.
And this is the phenomenon of superposition.
Wow. Yeah. Very hard to picture it.
Yeah, you can't. I accepted that I can't picture what does it mean in reality, because if you in our 3D world with the humans, it's very awkward to think that a human is I don't know, in a given state, in a given place, and also simultaneously in another place. It doesn't happen here in our world.
Yeah, in the macroscopic world, I think it's a bit hard to picture someone being in two different places at the same time. And
yeah.
And what are the challenges in quantum computing?
Well, there are a lot of challenges, and this is very good for researchers.
Yeah.
Because you can face different problems, and in this moment, quantum computing has a lot of problems that start from the hardware to the software to the algorithms. And so what we are trying to do in these years is to find the right way from an hardware perspective to build a quantum computer, and from the other side is from a computer science perspective is to find application, new quantum algorithms, and so algorithms that leverages the phenomena of quantum mechanics to provide some kind of advantage with respect to classical computation.
Yeah, so it's not just the hardware, but also the software needs to be basically rethought completely.
Yeah, totally, completely. Just to give you this intuition, so what's the workflow of a quantum algorithm. So in general, an algorithm is a sequence of steps. When you go in the quantum world, there are steps, but you have the power of quantum mechanics. And in this environment, it works like this. So you load your data in the quantum processing unit. The quantum processing unit executes the algorithm, and then at the end you sample the results. What does it mean? So in general, in classical computing, you provide your input to your algorithm and you obtain your output. But when you go into the quantum regime, you are dealing with quantum stuffs, and quantum stuffs does not manifest to the classical world. But we are human and we want to see the effect of this quantum algorithm. So to do that, we have this quantum algorithm that has that output a quantum state, but if you want to see this output, we need to measure. So the qubit collapses and you find out a bit, which is the classical bit that we use in classical computation. So this is the loop. You load your input, you run the algorithm, you measure the result. And you get at the end, you run this algorithm more than one time. At the end, you obtain a probability distribution that if you design very well your quantum algorithm, you will find a probability distribution that is picked on the correct output of your algorithm.
Okay, so it's not, let's say, intrinsically deterministic like a normal algorithm, but it's more probabilistic. But if you design it right, you will make it sort of deterministic, meaning that you will get the correct result with the highest probability. Kind of.
That's the point.
Okay.
Exactly.
Okay. Yeah, very, very, very interesting. And what are you focusing on in your research in this kind of huge landscape of quantum computing?
Yeah. So when I started my PhD at the Department of Computer Science, there was no one that already studied this stuff. So me and my supervisor started working on it. We studied from out of nothing, and we build our knowledge step by step. But at the very beginning, we observed that the part where you need to load your data into your quantum processing unit, it is demanding, and it is very crucial to give you a speed up with respect to classical computation. So let me frame better the point. Typically in classical computing, we when we do analysis of our algorithm, we say, okay, so it takes this time, it takes this space, and we have fantastic complexity bound on that algorithm. But you typically ignore what is the cost of loading the data in loading the input in your algorithm. So imagine that you have a problem typical of data science domain. So you need to analyze, to compute the variance over a very huge set of data. Then you need to find a way to load in a smart way in your PC, in your CPU, the data. And this happens also in quantum computing. So you need to find a way to prepare, so load data in the quantum processing unit efficiently, because it happens typically that when you read the research paper about a new quantum algorithm, they start with, we assume to have loaded efficiently the data in the quantum processing unit. But this is a very hard assumption. And if you have an algorithm that runs in log n time, so it means that if you have n as the size of your input, the time required to process that input given that algorithm is logarithmic in the input size. It can happen that the loading, for example, is polynomial in the input size, so like n squared. But if the input for the input you pay n squared and the algorithm runs in log of n, then the dominant cost is the cost of loading data in your quantum processing unit. So I'm working in this direction. What are the techniques that we can exploit to reduce the cost of loading data in your quantum processing unit to perform a given quantum algorithm? This is, let's say, the research trend that I started more or less 2 years ago. On the other side, that I still working on developing new quantum algorithms for AI typically.
Okay. Yeah, okay. Yeah, that's interesting. Yeah, I think it's actually another assumptions you said, because I mean you can have, I don't know, a fast car, but if it takes you, I mean it can run at, I don't know, the 1 kilometers in 10 seconds, but if it takes you 1 hour to bring it out of the box, that probably it's not very helpful, right? Okay. That's cool. And okay, and how do we solve this kind of loading into memory problem?
So this is a very good question, and it is an open question actually, for two reasons. One, because in this era, so if you Google the term quantum computer, you will find this huge stuff, this huge computer, which is actually a freezer, and on the bottom part of this freezer there is the chip, which is the quantum processing unit, but there is no memory.
Okay.
So if we as computer scientists, we are used to think about the random access model. So you have a CPU and you have a memory. And there are trade-offs. So typically, if you want an algorithm that runs faster, you need more space, and vice versa. In this era, we have a quantum processing unit, but there is no memory. And we are trying to develop quantum memories. So at the moment, quantum memories do not exist, more or less. But there are people that are working on creating those piece of hardware, and they are doing very great job. And so what you can do, from at least from my perspective, is to say, okay, so let's suppose that at some point in the near future, hopefully, we will have a quantum memory. But can I give some intuition to the people that are developing quantum memories, to give to those people some insight how I would like to have the internal structure of the memory, such that I can retrieve very fast information for the quantum processing unit. So there is like a loop. So they are developing the hardware, and the people that work in the how to organize the memory in a quantum memory can give them insight about what will be the a good structure of it, more or less. I simplify this thing. So at the moment, I'm really into this research field, and it is very, very challenging and interesting, because I think that this is the missing point to have the so-called quantum utility. So the moment where a quantum computer is going to deliver an impact on the society.
Yeah.
And there are a lot of people that have different opinion about this. Also, the definition of quantum utility changes according to the person that you ask it, but still it is more or less this concept.
Okay, yeah, cool. That's interesting, this kind of, feedback loop between, how I expect to use it and how you're gonna build it. So yeah, that's interesting. So, and you said you focus on these aspects, and so did you come up with some kind of, let's say, not design, but a way to use this kind of random access memory for quantum computing?
Yeah, so we designed a lot of quantum algorithms in these years, and typically they can run in the order of they can provide a time. We provided a time bound of logarithmic time bound in the size of the input. So what I try to do is to provide an access, a retrieval from this quantum memory that can be in logarithmic time. And at the moment, we have this work under review where we prove that we can do that in a time that is logarithmic in the input size. So at the moment, we would have a theoretical proof that we can prepare, so we can input the data into a quantum processing unit with in log time, and then we will have also an algorithm, a quantum algorithm that runs on log n. So the total complexity is it still keep to be polylogarithmic in the input size.
I'm curious. So all this work is, let's say, theoretical. So you don't have, of course, a way to try stuff for real because, you don't have access to a quantum computer. And of course, there is no quantum memory right now. So
what can happen in the future is to start a collaboration with those people that put the hands in the hardware. And probably it will be very interesting.
Yeah.
But at the moment, we are working from a theoretical point of view. Yeah.
And what do you see will be the, let's say, next steps in this line of research?
Oh, probably I think that the next steps can be to mimic what we have in a classical computer. For example, so we have this quantum memory, and if we pair with a quantum processor, we have the quantum random access machine model, which is the same of the classical world. But if you ask to yourself, so there is the memory in our classical computer, but also there are also caches, L1 cache, L2 cache, L3 cache. And so a thing that we are investigating is how can we manage the memory, the quantum memory, using a hierarchy of memories that start from, the quantum random access memory through L3, L2, and L1, and reaching the quantum processing unit. And so if you do that, then the next question is, so what is the policy that keeps data inside the cache L1 or move to cache L2, or even it discard totally the information? So this is the part that connect to the computer science world, while on the other side, it will be very interesting to develop with physicists, with engineers, how to realize a quantum random access memory. So from one side, we go to computer scientists, and the other side we go towards physicists or engineers.
Yeah, cool. And Alessandro, I have one last question that just popped up in my mind while you were talking about, the first, let's say, possible direction. Do you think we will need to mimic the current computer architecture, or like trying to get there with quantum computing, or maybe what we will need will be a totally different architecture that we are not kind of seeing now.
So, very good question, also this one. And what I would say is that we will not have a quantum computer that is going to take the place of a classical computer. We need to think to these tools as accelerators. So like the GPU is an accelerator for memory, for graphical stuff, and then for LLMs and AI-related tools. Well, I expect that a quantum computer is going to be an accelerator. For what domain, it is still unclear, but I think that we should look in the direction where you need to process a lot of data at a scale that is very, 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 very big. And I want to add also this parallelism. The CPU is very fast. The clock frequency is higher than the clock of the cores that are on the GPU. But we use GPUs because they allows us to run algorithm in parallel. So you have core in GPUs that have a lower frequency with respect to the classical CPU, but you have a lot of GPU cores. The same applies to quantum computers. The operation that you use to encode information or to evolve the state of a qubit, which is the quantum gate. Well, this is a slow operation, but still, if you have enough qubit, you can represent an exponential amount of information in the size of your input qubit that can be processed in parallel in superposition by your quantum computer. So I think that this is, let's say, the place where quantum computer will find them, where we will find them in the next years.
Oh yeah, it makes perfect sense. I mean, I'm a bit sad that I won't go around with my quantum laptop in the backpack. Would be cool, but yeah, apparently it won't happen. But yeah, still cool anyway. So yeah, Alessandro, thank you very much. I really appreciated the effort in making this kind of super complex topic very understandable. At least, I mean, I know nothing about quantum computing, but I was able to follow you very nice. So yeah, thank you very much for the effort.
Thank you, Luca, for inviting me. This has been a very cool discussion.
Yeah. Thank you. And yeah, cool. So, well, thank you everyone for listening. And don't forget to put a nice review for the podcast. And if you're a researcher, want to share your research, just, send me a message on LinkedIn or Blue Sky, or reach out to me in some way, and we will organize it. And in the meantime, thank you very much again, and see you at the next episode.